Okay, while the speaker is Yaodu Shu is setting up, he's going to be speaking about a new subtyping algorithm for system F sub with recursive types, and so it's a new take on a really classical problem. Okay, and I think he's ready to go.
Okay. Morning, everyone. Welcome to attend my talk, Recursive Subtyping for Alt. My name is Yaoda Zhou, and it's the joint work with Litao Zhou and Bruno Oliveira. The talk is focused on two type system features that has played a prominent role in object-oriented programming languages, recursive types and bounding quantifications. It's well known the recursive types by introducing the recursive operators mu to refer to itself could be used to model recursive data structures such as list and recursive object types. Bounding quantifications by allowing polymorphic variable to have a subtyping bound adjust the interactions between primitive polymorphism and subtyping. Since both recursive type and bounding quantification are two important features in OOP, it's natural to combine these two features together. Some lemma papers on the foundations of OOP, such as inheritance is not subtyping, F-bounded polymorphisms, the object encoding in the work about the object calculus, or essentially assume some F subvariant with recursive types. Even that at the time those work were published, no formulations was finished. Both recursive type and bounding quantifications are well studied. Recursive types have two flavors, depends on how you consider the relation between a recursive type and its one-step unfolding. One is recursive types, if we consider a recursive type and its one-step unfolding are equal. The other one is iso-recursive types. If we consider a recursive type and its one-step unfolding are non-equal but isomorphic. And to convert between the iso-recursive type and its one-step unfolding, you should have the fold and unfold operations, which takes a recursive type as annotations. Since we have recursive types, it's desired to have the recursive subtypings. The most famous recursive subtyping is Amadeus Cadeles Amber rules. And in 1993, they published a paper that discussed how to compare two recursive types in the similarity lambda calculus with top and bottoms. If two recursive types are subtypes, if their recursive body are subtypes, but assume the recursive variable are subtypes. Two recursive variables are subtypes if they are already stored in the context. And finally, two types are subtypes if they are equal, and two recursive types are equal if their unfolded trees are equal. The standard calculus with bounding quantifications called F sub has two common variants. The full variant called F sub allows the bound to be control-variant when comparing two universal types. However, the rich expressiveness of F sub results in the undecidabilities. There are many decidable fragments for the F subs. Among them, the most famous one is kernel F sub, which requires the bonds to be identical. F subs has lots of nice properties. One of them is that system F sub is conservative over system F. By conservativity, what we mean is that whether the extended system preserves the behavior of the original systems. We can map the types in the system F to the system F subs by set the bound of the thought for every polymorphic type variable. If subtyping and typing relations holds in the system F, they are also hold in the system F sub. if subtyping and typing relationships do not hold in system F, they do not hold in system F subs neither. After the meta-series of recursive ties and bounded F subs was established, some researchers tried to combine these two features together. However, Gallish shows that AK recursive types are non-conservative over a full F sub. Gallish shows counterexamples that you have two types A and A prime. Then A is not the subtype of the A prime in full F sub, but A is the subtype of the A prime in full F sub with AK recursive types. Besides, Gallish shows in the full F sub with AK recursive type, the transitivity elimination is invalid, and Pierce undecidability proof cannot be used in the system. There are also other works trying to combine the F sub with recursive ties. Jeffrey also tried to combine the F sub with AK recursive type, but is still non-conservative over F subs, and is semi-decidable. Semi-decidability means that if your programs terminate, it returns correct results, but the program may not be terminated. If we try to combine the kernel F sub with AK recursive type, we could get the decidable and transitive subtyping relations. However, all of those work are not modular. By modularity, so you have to modify F subs or the recursive type significantly. So you might also try to combine the F subs with isorecursive types. In the past decades, the most widely used subtyping route for isorecursive type is the folklore isorecursive AMBER rules. It's adapted from the Amadeo and Cadell's AMBER rules by setting the equality as the syntactic equalities. However, the lacking of the meta-series of folklore isorecursive AMBER rules is a barrier of its formalizations. The reflexivity must be built in, so without reflexivity built in, you cannot check that two equal contravariant recursive type are subtypes. And the transitivity elimination is non-trivial, so you cannot simply drop the transitivity route. The transitivity proof for the isorecursive AMBER rules is difficult. We only found one proof, and the proof is quite complicated. And finally, we cannot apply the isorecursive AMBER rules to the subtyping relations that is non-antisymmetric, such as record type and intersection types. So in our work, we propose a new calculus. Our calculus calls kernel F diamond mills modularly combines multi-field records and record types, so we can encode objects. And the subtyping relations is non-antisymmetric. We have the bounding quantification, so we choose the kernel style F sub because we want to make the whole system decidable. Since the subtyping relationship is non-antisymmetric, instead of the equal bond, we choose the equivalent bonds. We have the isorecursive subtypings, and here we choose the nominal, recently developed nominal unfolding rules. We have structural folding and unfolding rules. And finally, we have the additional lower bounded quantification and bottom ties. So for every polymorphic type variable, it can either have a lower bound or an upper bound. We choose the nominal unfolding rules for comparing two isorecursive types. The nominal unfolding rules was proposed last year by me and my co-authors, which shows that the nominal unfolding rule states that if two isorecursive types are subtypes, we just need to check if their recursive body substituted by the recursive body for the recursive variable with extra fresh label alpha. Here we mark the alpha by the red colored subtypes. The nominal unfolding rules is to prove that has some expressiveness as the iso recursive amber rules in symmetry lambda calculus with top, while has the advantage of enabling modular proof. So you don't need to change the existing proofs. You just have an extra case for recursive types. And we can have easy transitivity proof, and we don't require the reflexivity built-in. And most importantly, we can apply our nominal unfolding rules to the subtyping relationship that is non-antisymmetric, like record and intersection types. We also generalize the folding and unfolding rules, and we prove that structural rules are type-solved. In conventional folding and unfolding rules, the annotated types must be a recursive types. In the structural folding and unfolding rules, the annotated types could be, for the fold operation, could be the subtype of a recursive type. And for unfolded operation, the annotated type could be the subtype of a recursive type. Our calculus have some nice properties, namely type soundness, decidability, and conservativity over F sub. We prove that our type system is type solved by proving the persuasion and progress theorems. For proving the persuasion theorems with conventional folding and unfolding rules, you must to prove that our subtyping relationship have good such properties. It says that two iso-recursive types are subtypes, then there are ones that unfolding are subtypes. In previous work is called unfolding lemmas. In our calculus, we use the structural folding and unfolding rule. So we have structural unfolding lemma. It says that two iso-recursive types are subtypes. Then there are ones that are unfolding, but using supertype and subtypes is respectively as subtypes. Both kernel F subs and nominal unfolding rules are proved to be decidable by a measure approach. In our work, we integrate these two approaches into one. Concretely, we have a size function to compute the size of the types. So under the context per size, in the context per size, we compute the size for every type variables. So for the universal types, we just sum up the size of type bond and type body. For recursive types, we compute the size after the nominal unfoldings. We also have evoke functions to recursively compute the size for every variable in the context gamma. So we have lemmas says that if size of A is under the initial context evolve gamma plus size of B under the initial context evolve gamma less or equal than case, then A is the subtype of B under the context gamma is either true or not. By the induction on case, we prove that our type system is decidable. We also prove the F diamond mills is conservative over kernel F sub. Formally speaking, let gamma A, B, M, E be in the language of kernel F subs, and they are well formed. So if A is the subtype of B under the F sub, if and only if A is the subtype of B under the F diamond mills. E has the type of A under the language F sub if and only if E have the type of A under the F diamond mills. Our calculus is very expressive. Here I will show an example how to encode the subtyping between algebra data types in our calculus. It's well known that Church encoding can be used to encode algebraic data types. But unfortunately, some operations have poor performance. For example, the implementation of predecessors of natural numbers causes linear time, so Church encoding is not perfect. One of the alternatives of Church encoding is Skok encoding. In the following, which shows that with polymorphic types lambda calculus, recursive type, and subtyping, we can encode subtyping between data types with high degree of composability and decoupling of components by extending the Skok encodings. Firstly, we define a data type ESP1 with numerics, addition, and subtraction constructors. Then the encoding of this data type is defined as a recursive type whose body is a polymorphic higher order functions that takes a record with 3 fields as input. Each field corresponds to a constructor in the data type definitions. To construct concrete instance of the data types, each constructor also comes with a corresponding encoding in the calculus. To write a function that performs case analysis on the data types, one can unfold the recursive types, extensions A with the result types, and then provide a record that maps each case to its implementation functions that takes the constructor component as input and return a result of type 8. You can construct the expression 1 plus 2 directly in our calculus and get the results by calling the evoke functions. Now, consider a larger data type ESP2, which extends the ESP1 data type with a new constructor next for denoting negative numbers. The data type ESP2 differs from ESP1 only in the new constructors. Other constructors are just the same. Note that ESP2 has more constructors than ESP1, so it should be safe to call ESP1 expression into ESP2 expression. So you can check that in our encoding, ESP1 is the subtype of ESP2. The most obviously benefits of the subtyping between algebra data type is that it reduces code duplications. For example, one can write a pretty printer function of the expression tools that return the string form of these expressions. And with this function defined and subtyping relations, that ESP1 is the subtype of ESP2, we can simply reuse the function to print ESP1 expressions. Interesting point is about the polymorphic constructors. Now we have 2 data types and share most of the constructors. To reduce the code duplications, the polymorphic constructors are decided. We have seen ESP1 is a subtype of ESP2, so here we expect a polymorphic constructor that works for both data types. We take the add constructor, for example. That is our desired typing and definitions. To make this encoding happens, there are 2 major issues we need to take care of. Firstly, now we are employing the lower bounded quantification, while in traditional F-subs, we only have the upper bound quantifications. Secondly, to get the desired typing, we would like to fold the constructor into a lower bound type variable E, which is the subtype of the recursive type ESP1. That's where the structural folding rules we have mentioned before play a role. Another benefit is that precise typing information is preserved in the percent of the code reduced. Suppose we wish to implement a disregard function that transforms ESP2 into ESP1. by transforming the negative numbers minus n into the subtraction yield subtract ends. This function should have a desired precise typing as ESP2 to ESP1. However, in a typically functional language, without typing between algebra data types, the precise typing comes at a cost of code duplications. One might need to define ESP2 and ESP1 separately to get a desired typing for disregard functions. But since the constructors for two data types are different, many other operations such as pretty printers need to be duplicated. One could of course only define ESP2 and type disregard with the imprecise type, so the pretty printer functions does not need to be duplicated, but we lose the static typing information. Our disregard solution is simple as shows that we can see that with polymorphic constructors, we can avoid queue duplication and obtain static typing guarantees at the same time. In summary, in our work, we propose a new solution to combine the bounded quantification and recursive subtypings. And our type system has many nice properties, namely type soundness, decidability, conservativities over F subs, and we saw useful applications that we can encode subtyping between algebra data types. Finally, all theorems in our papers are formalized in the corpus. That's all of my talk. Thank you.
Okay, we have time for one or two questions. So does anyone have a question?
Thanks. This is cool work. I suppose this is the obvious question, but how would could you transport some of your results to an equirecursive setting? And in that situation, would you be able to do similar things?
I have to say the subtyping, our subtyping rule is less expressive than recursive subtyping rules. So maybe but without subtyping, the recursive subtypes have sense are semantically equals to the iso-recursive types, but for the subtyping, the expressiveness are different. So actually, I don't know how to convert our result to recursive settings.
Hey, how are you? Can you go back to the slide on the decidability of your subtyping relation? Using the size, I think you might have passed the size. Here we go. The bottom statement there, you're saying that if the size of A and the size of B, basically the size of those, the A is decomposing that type, is less than or equal to K, then the assertion is either true or not? Like, if the size is less than, is that a classical statement? Like, is that, then we know it's either true or not, or we know which one it is, right? So, okay, let me rephrase. If the size of A is less than the size, plus the size of B is less than or equal to K, then we know that A is less than or equal to B. This is the assertion. Then we know that the consequent holds. Is that?
Well, so
find other ways to be confusing.
So if you look at our size functions, it always decrease. The size of the conclusions always larger than size of the premises. So you can, that's why you can induction on Kate.
Okay. I'll leave it there.
Okay. This is a constructive statement. It is a constructive statement. Okay, that's okay. Yes. Okay, I will ask the last question here. So in your typing rule for fold.
Typing rule?
Yeah. it looks like you have to, I guess also for Unfold, you have to invent some of these types. So is there going to be some issues with type inference when you implement it?
We don't have any type inference.
Oh, okay.
But actually we. I say so. We propose algorithmic typing rules, so you don't need to deal with the subsumption rules.
Okay. Thank you again.